Alright, right off the bat, before we start, I guess I sort of assumed, maybe mistakenly, that you had an idea when you clicked on this video about A-star pathfinding already, but on the off chance that you don't, the A-star search algorithm is an algorithm that tries its best to find what is the cheapest possible path between 2 points, in this case on a grid, and it can do so around walls, and at the end I'll show some examples with mazes. If you haven't already looked at the watch length of this video and clicked away, I'll have put a couple of resources in the description so you can have a better understanding of the theory before we talk about more of the hard programming for the rest of this video. Alright, so as you can see here, I don't have much already placed in this scene. All that I have is something that's instantiating a grid, and you can select certain cells in that grid and they'll just turn black, and you can basically paint with cells in this grid. So to start off, I'm going to go ahead and I'm going to make an A-star pathfinding script, and it's not going to have any mono behavior. It's not going to have any mono behavior, which means it's not going to derive from a game object at all. It's not going to be placed or inherit any of the game object functions. So I can go ahead and delete all of those. So I'm just going to go ahead and I'm going to make just a simple function to begin with, and we'll call this public list of vector2. So we're going to say that this function is going to return a list of vector2 ints, and that'll be our path. Which coordinates to go to on my grid. It's going to return a list of vector2 ints, and I'm going to call this pathfind, if I can spell. And it's going to take two things. It's going to take two vector2 ints. It's going to take a vector2 int called, let's see, we'll call this origin, and it'll take a vector2 int called goal. Alright, so now outside of this function we're going to declare some variables. Just so that we can use some of these further out in other functions, I'm going to go ahead and make a public, let's see here, vector2 int. I cannot spell. I'm going to make a vector2 int called origin. I'm going to use a capital O just to keep this easy for myself, and then another vector2 int with a capital G for the goal. That way, in functions that are not this pathfind function, we can actually reference these variables, which will be nice. Origin equals the lowercase origin, and goal with a capital G equals the lowercase goal. So that'll just be nice. We'll go ahead and say globalize functions variables. Alright, so I'm also going to create a new class. Actually, this has to be outside of A-star pathfinding. I'm going to go ahead and call this public class node. Node is going to hold all of the values for us that we're going to need, and each of these nodes, we're going to have an array of them. Each of these nodes is going to correlate to one of the grid squares, and this is just going to hold a ton of information for us that's going to be useful to know when we're doing the A-star pathfinding. So we'll make a public, let's see, we'll call this gcost. That'll be a float, public float gcost, a public float hcost, and a public float fcost. Those are just straight off the bat really important for the math. We're also going to make a public vector2 int coord, so coordinates, so where it actually correlates onto our grid. And then we're going to make a public node previous node. And this will be important to trace backwards, back to the origin when we're actually building our path at the end. And we'll just go ahead and say public node gcost equals 0, hcost equals 0, fcost equals 0. We won't actually instantiate the coordinates, and I think the node is going to start off being null, but we'll go ahead and do that anyway. Equals null, just for safekeeping. I don't want any errors to happen. So now we've got this class of things called nodes, which we're going to create an array of. So here we're going to make a public, let's see, we'll say node. We'll make an array and we're going to put an apostrophe in there. So that's going to be a two-dimensional array. And we'll call this node grid. So this is going to be our grid of nodes. So when we actually call the pathfinding function, we're going to go ahead and instantiate the node grid. Alright, and to do that, we're going to go ahead and create two for loops. You can tab and it'll actually make this a lot easier for us, but we'll go ahead and do x there, and we'll make this. What we need is the grid, right? We need each node to correlate to a certain cell in the grid that we've already created. So I could, and you could, create references however you need to actually find whatever your grid size is, or any other method that you're using to actually use this method for pathfinding, but I'm just going to go ahead and force myself to add another parameter. Know that you don't actually need to do this if you're going to find your grid size in some other way, if it's static or more easily accessible than from our grid script. So I'm going to go ahead and make another vector2 int, vector2 int, and I'm going to go ahead and make this a grid size variable. We're not going to need that to be public, I don't think, although I will, just for safety, public vector2 int grid size. We'll make this one have a lowercase g, so we can continue our pattern, and then we'll make capital grid size equal to lowercase grid size. Alright, just in case we need to use that later, and we'll make this, say, grid size dot x, x++, and then inside this for loop, we're going to go ahead and make another for loop, and we're going to use y this time. So this is going to be our x and y variables, and we'll have this only continue if y is still less than grid size dot y. Alright, so now we can say node grid x and y equals new node. And we don't need to do anything except put in its coordinates right now. None of the other variables are something that we're going to edit straight from the very beginning. So we'll go ahead and say node grid x, y dot coord equals new vector2 int, and it's going to contain our current x and y variables. Just something that's easier to reference for us when we're passing this back through the function. So then I'm going to go ahead and, when we're instantiating the grid right before we do the for loop, I'm going to go ahead and say node grid equals a new node two-dimensional array, and its dimensions are going to be of size, grid size dot x, and grid size dot y. So now what should happen when we run this function is we should have an array, a two-dimensional array of nodes, which all contain a new node and their correct vector2 int for their coordinates. Alright, so now we're just going to create a couple of functions which we can use to calculate all of the costs that we need for each node. We're just going to get these out of the way now, and we're basically going to reference them for every node each time we analyze them. So we're going to go ahead and say public void calculate costs. And what we'll do right now, like that, what we'll do right now is we're going to go ahead and make everything static. Because I want to be able to reference this from anywhere, and they're not going to be, because it's not mono behavior, I don't really care whether or not there's going to be separate instances of this pathfinding function. You might, but for me right now, just so I can reference it easier, I'm going to go ahead and make everything static. Okay, so now that everything's static, I'm even going to put a couple of functions in the calculate costs function just to make this super easy for us. We're going to go ahead and make a function called, let's see, calculate gcost, and we're going to make a function called calculate hcost. And what we're going to do is we're going to make all of these require us to put in a node. We're going to go ahead and name it node, just so we can reference it easier. And, nope, node, and then we'll say node.fcost is equal to node.gcost and plus node.hcost. Okay, so now that our fcost is equal to our gcost plus our hcost, let's go ahead and make these calculate cost functions. So if you remember, the gcost is the cost of going from the origin to the current selected node. So we're going to obviously be using this vector2 origin, which is the reason that we globalized it, that we made it accessible from other functions. We'll make this a public static void, and we'll just call this calculate gcost. So we can use that from above. And obviously this is going to take node, we'll call it node. Alright, so now we can calculate the gcost. We'll go ahead and make another public static void calculate hcost. And we'll also require this to take in a node, we'll call it node. Alright. So now these two functions are basically going to allow us to calculate the cost for them and then also pass them in to calculate the fcost. So this will just do everything for us. All we need to do is call the calculate cost function. Alright, so in our calculate gcost function, the gcost is going to be the cost in cells, in points, that it's going to take for us to get from the origin to the current node. So this node referenced right here. And the way that we're going to do that is we're actually going to get the gcost of our previous node and then add to it either 10 or 14, depending on if you're going diagonal or if you're going in one of the cardinal directions. So right off the bat, what we're going to do is we're going to have to find the previous node's gcost. So we're going to say gcost, or node.gcost, .gcost is equal to node.previousNode.gcost. So we're going to inherit the gcost of the node that came before us. And then we're going to go ahead and add 10 or 14. So how do we know which one to add, either 10 or 14? For me, what I ended up doing in this situation is I'm going to try and find the diagonals first. And if we need any diagonals, we'll add 14. And if we don't need any diagonals, we'll go ahead and just add 10. So what I'm going to do is I'm going to go ahead and find the difference. So vector2 int diff for difference is equal to our current node's position, node.coordinates, minus the position of the previous node. So minus node.previousNode.coordinates. So this should give us something that looks like maybe -1, 1, maybe 0, 1, something like that. Alright, so now I'm going to find our cardinal directions and our diagonals. So the way that I'm going to do this is I'm going to go ahead and say if difference.x is equal to 0, or, and you can do or with the two vertical lines, or if difference.y is equal to 0. I need two equal signs. So what this is going to do is it's going to say if we are only moving in one of the directions, then we're going to just add 10, right? So the gcost, node.gcost plus equals 10. Next, all we have to say is if you're not moving in a cardinal direction, you must be moving diagonally. So we'll just go ahead and put an else in here. And we'll say if you're not moving in one of those cardinal directions, you have to be moving diagonally. So your gcost is going to increase by 14. Now we're going to calculate our hcosts. And this is slightly more complicated. It will be a little bit longer, but it's not anything different. It's just going to be finding the difference between our goal and our current node. So we'll make a difference value again. We'll go ahead and say vector2 difference is just going to be equal to our goal, which we have globalized, minus our node dot coordinates. So this is super simple. All we're doing is finding the difference between them. And we're going to use the same method here to figure out how much it's going to cost. And we'll use this with a couple if statements. So think of it this way. If you're moving to the right 5 and up 3, then 3 of those can just be diagonally. And in other words, whatever the smaller value is, x or y, whichever the smaller one is, will all be diagonal, and then whatever is left over you can have be straight directions. That will always be the fastest way, assuming that there's no walls. To do that, we're going to need some absolute values. So I'm just going to go ahead and say diff equals new vector2 int, and its x is going to be equal to the absolute value of its original x, so diff.x. And its y is going to be equal to the absolute value of its y. So now we should only ever have zeros and ones. This should effectively be a two-dimensional binary vector2. So we'll say diff.y. So now what we're going to say is if x is less than y. Whoa. If diff.x is less than diff.y. That means that in this example, maybe you're going to the right 3 times, but you're going up 5 times. So 3 of those can be diagonal, and the other 2 are going to end up equaling 10. So we're going to have our h cost equal to, let's see, h cost is going to be equal to the smaller one times 14. So diff plus equals diff.x times 14. And then we're going to subtract x from y and then multiply that by 10. So node.hcost plus equals diff.y minus diff.x times 10. So that's going to give us that value. Otherwise, if diff.y is less than diff.x, we'll go ahead and do this exact same thing and just switch around the x and the y's. So in this situation, we're going to go ahead and multiply 14 by the y, because the y is smaller, and we're going to subtract the y from the x. And again, this should be true if they're equal to 14. And the only case where this actually won't follow through is if they're equivalent. And the interesting thing about them being equivalent is, we'll say else if they're equivalent, we don't really care which ones we're going to multiply by 14. Because if they're equivalent, you're going to be able to move diagonally the entire time. If you're moving up 4 and down to the right 4, move diagonally 4 times. So if diff.x is equal to diff.y, we're just going to move diagonally equal to arbitrarily one of them. I'll just select diff.x. So hcost is going to be increased by just one of them, right? So diff.x and then times 14. So this should give us an accurate hcost now. And then the last thing that I'm going to do here is I'm just going to go ahead and make sure that it's set equal to 0 at the beginning. So node.hcost equals 0. So now we can calculate our g-cost, and we can calculate our h-cost, and we can calculate our f-cost here by adding the two of them. So we're going to run this for every node when it gets to that node's turn to run. Okay, so now we're going to move on to the next step. And this is some theory in the A-star pathfinding, but what we're going to do is we're going to create 2 lists of nodes. And it's going to be our open list and our closed list. So our open list is going to contain all the nodes that are adjacent to nodes we've already analyzed, but that have not yet been analyzed themselves. And all of the closed nodes are going to be the nodes that we've already analyzed. So what that's going to do is it's going to make sure that we don't loop back over our current path, or that we don't go through the same thing again. So we're going to go ahead and say open nodes, and we're going to make a static list of nodes called closed nodes. What we need to do is instantiate them in the same way that we're instantiating the node grid. So we're going to say open node equals new list of nodes. And closed node equals new list of nodes. All right, these are going to be empty to start off with. So we have this situation right now where we can calculate all of our costs, but here in the calculate gcost function, it requires that that node has a previous node attached to it. And the only node where that won't be true is the origin. So we need to analyze the origin manually. So we're going to go ahead and analyze the origin. The interesting thing about the gcost of the origin, though, is that it will always be 0. So we're going to go ahead and say node grid origin.x origin.y. So this is the node at the origin, and its gcost is just going to be equal to 0. We can calculate its hcost using the same thing, because the hcost doesn't actually require that we have a previous one. So we're going to say calculate hcosts and we're just going to plug in our origin node, and it's going to calculate the origin for us. And the last thing that we're going to do is we're going to go ahead and add this to our OpenNodes. So OpenNodes.add this current origin node. All right. So I need to go ahead and create an analyze node function. And this is going to be the most important function in our A-star pathfinding method. So I'm going to go ahead and create a public static analyze. Is that spelled right? I don't know. Analyze node. And obviously this is just going to take in a node. So we're going to go ahead and, there we go. Public static void analyze node, and it's going to take in a node. So we're going to go ahead in here, and we're going to say closed node dot add the node that we just put in. We don't want to be analyzing this node anymore. And then we're going to say OpenNodes dot remove that same node. We want it to not be in the open nodes anymore. After that, we're going to go ahead and, just so that we can have a little bit of easier looking programming here, some more simple looking programming, we're going to go ahead and set a variable called coordinates, or coord, and we're going to have that equal to our current node's coordinates. Just something that's going to be more easily referenceable. And now we're going to go ahead and actually loop through all adjacent nodes. So let's go ahead and let's create a little bit of for loop situations, and we're going to start with x at -1. We're going to start with x at -1, and that's because we're going to go from 1 to the left to 1 to the right. So it's going to be from x of -1 to x of 1. That used to be an equal sign, to x of 1. And then obviously we're just going to x plus plus, like a normal for loop there. Let's go ahead and format this a little bit better. I don't like for loops that are nested, to have those brackets like that. So I'll make another for loop for the y, same situation. The y is going to start at -1. And then if it's less than or equal to 1, it's going to continue, and y plus plus. Alright. Now inside this for loop, we're going to have to find whether or not it's within the bounds of the grid. Because we don't want to, if we're in the bottom left-hand corner, we don't want to be analyzing a node to the left, because there isn't one there. And we'll go ahead and we'll get an error. So we'll go ahead and we'll make a little bit of an if statement to make sure that that's not going to happen. And we're going to go ahead and say if coord.x, so if our current node's x coordinate plus x, which is the offset value, is greater than or equal to 0, then we'll allow it to pass through. And then we'll say and if coord.x plus x, so if our offset is less than the grid size. So we have that variable under grid size x. So as long as both of those things are true, we can pass through the if function, and we'll do the same thing for y. So if the coordinates of the y of our current node plus our offset value, which will be somewhere between -1 and 1, is greater than or equal to 0, then we'll allow it to go. And if the node that we're analyzing, the adjacent node that we're analyzing, so coord.y plus our offset, is less than the grid size.y. then we can pass through the if statement. Alright, so once we're in here, this is going to be every cell that we need, and we're going to put, I'll mark it right here, we're going to put a limiting function, or I guess limiting statement, to check for walls. Right here, that's where this will go. But for right now, I'm just going to go ahead and say if close nodes.contains the current node that we're analyzing, so node grid chord.x plus x chord.y plus y, then do nothing. Else if we're going to do the same thing for OpenNodes, so OpenNodes.contains node grid the current node we're analyzing, chord.x plus x and chord.y plus y. It's going to do nothing, and then we'll go ahead and say here else. And within this else, so this is checking to make sure it's not in either of these. There's a couple of ways you can do this with the AND statement, but it gets honestly a little long, and I'd like to be able to do stuff in these if I need to. Let's see, how many of these am I going to need? Oh, that's not supposed to be here. Here we go. I want to be able to do things in here if I need to, but otherwise, inside this else function, if it's not closed and it's not open, then we're going to put it into the OpenNodes. So OpenNodes.add the current node that we're talking about, so our node grid with coordinates.x plus x and coordinates.y plus y. We're going to go ahead and add that to the node We're also going to make sure to set the previous node of our current one to the node that we pass through the function. So every adjacent node should feed back to this current node. So we're going to go ahead and say node grid chord.x, chord.y, sorry, chord.x plus x, chord.y plus y. That previous node is equal to our current node. So we want to make sure that they can all trace back to their origins. And then for these nodes, we're going to go ahead and calculate their costs. So we can just pass in a node, and that'll be node grid. That'll be this node. That'll be our node grid chord.x plus x, chord.y plus y. A couple of sirens. Alright, so we're going to go ahead and do that. And now it's going to, for every adjacent node, calculate their costs and add them to the open node grid and set their previous node to the node we have set in the beginning of the function. Alright. So now we're going to make a while loop, and we need this while loop, so let's say loop while we have not found the goal. So we're going to continue through this loop while we've not found the goal. So what we can say is while OpenNodes does not contain, and then our node grid goal.x, goal.y. So while our node grid, while our OpenNodes does not contain our goal node, we want to continue to loop through this function, and inside this function we're going to analyze the smallest node. So I'm going to go ahead and say analyze node, and we're going to want to analyze the smallest open node. So I'll make a function for that, and I'm going to go down here below analyze, make a function called smallest static. It's going to return a node, so static node, smallest open node. Alright, so what this function is going to do is we're just going to simply find which node in the open nodes has the smallest f cost. So we're going to start off with a float I equals math f.infinity, and this strategy is going to work for any finding the smallest function. Right now we're just going to use it for nodes. We're going to make a node, small node, equals null. And then right here we're just going to say for each node in OpenNodes, if node.fcost is less than I, we're going to set I equal to node.fcost, and we're going to set small node equal to node. And at the end of this, we're going to go ahead and return small node. Alright, so that's going to find the smallest open node for us and analyze it while we've not found it. So this should basically create our path. It's going to find all of our nodes up to the goal node, and then it's going to have the previous nodes be tracing all their way back to the origin. So now what we need to do is actually build that backwards. So I'm going to create a function called build path, and it's going to take in a node. So we'll build path from the goal node. So node grid goal.x, goal.y. So we're going to build a path from our goal node. I'll go ahead down here, I'll make the build path function. Build path static. Doesn't actually need to return anything. We're going to build a path. To start this off, right before we actually do anything in the function, we're going to go ahead and make a static list of vector2s. Vector2 ints, because that's what we happen to be using right now. I'm going to call this pathway. And this is going to be the actual thing that we return. And then under here, let's just go ahead and instantiate that. Make sure that it's clear and instantiated, so we don't have any errors there. So pathway equals new list of vector2 ints with nothing in it. All right. So now in our build path function, which requires a node, there we go. In our build path function, what we're going to do is we're going to start from the goal and we're going to work backwards. So we've got the situation right now where we need to be adding the current node, so node, and then their coordinates, which is our vector2 int for that node. So we're going to add the coordinates, and then we're going to say if the current node being analyzed, if its previous node is our origin, which means we've made it all the way back, origin.x, origin.y, if we've made it all the way back, then we simply need to add the origin, so pathway.add node.previous node.coordinates. We're going to add the origin to it, and we're going to reverse the pathway, so pathway.reverse. And this is just so that we can call it from the bottom up as opposed from the top down. And if this isn't true, if we've not already made it all the way back to the origin, we're going to go ahead and say else. If this isn't true, build the path, continue to build the path, except now our node is going to be the previous node. So it's going to build the path again with the previous node, and it's going to keep looping through this until we've gotten to the origin. So now I think all we need to do is return pathway. Didn't spell that right. Return pathway. And this function should, given these variables, return the pathway. Alright, so I created a small script here. This is just going to be a mover. I'm going to go ahead and put this on a cube so we can use it for debugging purposes. And it just finds whether or not it has a pathway, and if it does, loops through all of the vector2s in that pathway and finds its way to each of those sequentially, given a move speed. Alright, so now we've got a pretty large grid, and our cube here, this little mover, can find its way to any of the cells that I ask it to because it builds the pathway. Over here in our grid script, when we click, it's just going to give the mover a movement based on our A-star pathfinding class. So this is just returning the vector2 int that we created in here and passing it back through into the mover, which it uses to move to that location. So the next thing that we need to do is we actually want it to be able to move based on these walls. So right now I can paint a wall, but he'll go right through it. He actually doesn't care. And that's pretty simple. If you remember, we put this here to limit for it. Let's go ahead and tab these all up a little bit. And right here, we're going to go ahead and create an if statement that's going to check for the walls. And it's not going to add walls to the open nodes, which means we're not going to consider ourselves able to move through it or into it. So we're going to go ahead and say we're going to reference our grid. So we're going to say if GameObject.findObject of type, And you can do this in any other way. All you need to be doing is referencing the cell and whether or not it's movable. For me, I reference that by finding my grid script and figuring out whether or not that cell is black. So if grid script.cells chord x plus x chord y plus y. So if that cell, if it's get component, this is really crude. You might have a better way to do this, but for right now, just for purposes of this example, I'm going to go ahead and say if its color is equal to color.black, then I don't want any of this to happen. So I'm going to go ahead and add the not operator in front of this. So if this isn't true, if it's not black, then we can continue. Otherwise, it's not going to consider it inside of here. If not, game object define. Wrong place for the not operator. I'm going to go ahead and put the not operator right here. So if it's not black, then it'll continue through this code right now. So I should be able to save this. I'm going to paint a little bit of a wall here. And he should go to this location around my wall. The only thing that this script isn't going to be able to help out with right now, we can add a little bit of math to figure that out, is your cube will actually be able to move through diagonals like that, because if he's standing right here, he can analyze this node since it is technically adjacent. And you can check for things like that, that's just a little bit of math. Alright, this is a little editor's note here. The reason that we left this open, we were supposed to be doing something in this, and I'll do that right now. In here, what we're going to say is, if we're going to analyze a node, and it's already been analyzed, or I guess it's already adjacent to a closed node, as in it's already open, we want to make sure that it's got the lowest possible G cost that it can have, or else our F costs aren't going to be very accurate. So the way that we can do that is we're going to say if our current node, if the node that we are analyzing all of the adjacent ones of, if this one right here, if its G cost is less than the G cost of the previous node, so the G cost of this node's previous node, we want to make sure that we're going to convert it to have its previous node be this node. We want it to come through the cheapest possible G cost, and we can do that super easily. We'll just say node grid.previous node equals node. And then if you want to do some debugging, or if you need the final G cost to give you something like an AP score, an action point score, something like that, we'll just go ahead and recalculate the costs for this one. Since its G cost is based on the previous node, and we just changed its previous node. So this should give us the cheapest possible option for anything like that. So now our code runs pretty nicely. I can draw something like a wall here, and he'll find what I think is, and what I'm sure is, the cheapest possible path to any single point. And if you wanted to, you can come here in the code, and you could define something right here before the build path that's going to give you the G-cost.log. It's going to give you the G cost of the goal, and this is how you can actually determine some of these pathways and whether or not they are the cheapest possible path, or if you need to use that for something like an action point system, like I said. So here we go. If I draw this path like this, and I place this here, you can see it's going to actually display for us the G cost. And if I go between 2 points here, this is how you can make sure that we did our final math correctly. If we go through 2 points here, the G cost is always going to be the same. That's how we can sort of moderately be sure that it is finding the cheapest cost between these 2 points. It's not finding something different both times. So hopefully you now have a little bit of a better understanding about how to write your own A* function in Unity. And if you've miraculously made it to the 40-something minute mark, I really appreciate you watching. Have a good one.